welcome back. In this video we're going to be taking a look at a set of vectors which I've described here as W, and we're going to go ahead and prove that it's a subspace of three-dimensional space. And to do that, we're not going to show that it's a full vector space. We're going to take advantage of the subspace test, which I've rewritten down here. It says if you start with a vector space, so V is our vector space, so we'll be thinking of V as being three-dimensional space. And then a subset, so a subset is just some collection of vectors that is in the larger space. So this W is the same W. A subset is a subspace if the three are true. So a subset is a looser term, subspace is a more precise term, and it works if you just show these three things. So one, that there's something in there, it's not empty. All right, one typical way to do this, so typically this is done by showing that the zero vector is in W, right? That's usually a pretty easy one. Then we want to show additive closure, which is this part 2 here, and then part 3 is scaling closure. So if we have just these three things, then we know for certain that W is a subspace, right? So in particular, then W is in fact an entire vector space on its own. All right, so let's go ahead and get started with the proof. We'll do it in pink. So let's go ahead and let V equal three-dimensional space and W be that collection of vectors described above, which we're repeating here so that we know precisely what we're talking about. So with that, we then want to show each of these properties. So first off, let's just note that it is indeed a subset. So notice W is a subset of V, as every vector in W has three entries. Excellent. And now, what do we want to do? We want to show that it's non-empty. So 1. So again, maybe I won't use the word notice again, but let's try look. The zero vector is equal to, well, let's try and get it in the form of W up here. So we want to find some A and some B that make this equal to 0. And well, certainly if we take A and B to both be 0. So the zero vector is in W, and W is not empty. So that step's pretty easy to complete. Right. So for step 2, the additive closure, we want to start with two vectors, let U and V be in W. So because we know what W looks like, we can write U as A plus B, 3A, A minus 2B, and V, well, we can't use A and B again because they're already taken, so let's just go on to the next letters in the alphabet. 3C, C minus 2D. We want to make sure we're in the same format as we were for W. So we want whatever's the middle piece to be 3 times the thing and the D. So yes, those are both in the forms of W. So where A, B, C, and D are all real numbers. Okay, so again, we introduce new variables, so we should indicate what they are. Now let's go ahead and compute the sum. U plus V, which we already said what U and V are, so we can substitute these vectors in. So again, that's substitution, so let's remind ourselves. Then we can actually use the addition to get that this is A plus B plus C plus D, then 3A plus 3C, and then A minus 2B plus C minus 2D. This would be our definition of addition in R3. And now, this is where we want to get this rearranged so that it looks exactly like it's in W. So we want, again, let's remind ourselves, we want the second entry to be 3 times the first thing that we write there. And then the third entry to have that same thing minus 2 times something else. So let's go ahead and rewrite this. So we notice that the middle entry is going to look like 3 times something. And then that something should be the first thing we see here. And then everything else will go there. And then again, we want that thing to be the first thing in the third coordinate. And then we want minus 2 times something, and that something should be b plus d. Right. So let's notice that this thing should be the same as this one, and the a plus c should be the same throughout as well. So this is associativity and commutativity in R. And let's just hammer it home that we indeed have the right form by replacing these things, x minus 2y, where again we introduce new variables. X is a plus c and y is b plus d. Thus u plus v is in w because it has the appropriate form. Right. So that's our additive closure. We then want to go ahead and show scaling closure. So well, we already have u, so we can use the same u. So let u equal to a plus b, 3a, a minus 2b as above. But now we need a scalar, so we need a new letter, and e be a scalar. So now we're going to go ahead and compute again. We want to compute the scaled version of u, and again we want it to end up being in the correct form. So that's an e. Alright, so that's e times a plus b, 3a, a minus 2b. Again, using substitution, I'll write in the reasoning afterwards so that I don't have to switch pens all the time. So e times 3a, e times a minus 2. So we have our definition of scaling. And then again, we want the middle term to be 3 times something. Okay. Then we want to separate that something in the first part from the other stuff. And then we want that same thing minus 2 times something. Oh, I missed the b. 2eb. Right, so again, this is of the correct form, so it's z plus w, 3z, z minus 2w, where z is ea and w is eb. Thus, c times u, or e times u, sorry, is in w as it is of the correct form. Excellent, so we're not quite done yet, so we showed all 3 steps, so now we just need to throw in our conclusion sentence. So let's go ahead and do that at the bottom. So therefore, by the subspace test, we need to mention that we're doing that at some point. Subspace test, W is a subspace of R3. And that is it. There's our proof. Alright, so this is a very important kind of proof, so thanks for watching, and be practicing these subspace proofs as much as you can, because they are absolutely the most important ones. Hint, hint. Alright, have a good one, enjoy, bye-bye.